Suppose that x1 to xn are IID with density little f and CDF capital F, exactly the setup that we discussed in the last video. Now our aim is to find joint density of all the ordered statistics together. Earlier we did it separately for this and separately for that. Now we want to get all of them, x1, x2, etc. up to x round bracket n. Now there is a particularly simple formula for this joint density, but let us warm up with some simple example first. Here I have taken only x1 and x2, that is n equal to 2, their IID with etc. Now I consider only x round bracket 1 and x round bracket 2 and let gxy be their CDF. My aim is to partially differentiate capital G with respect to x and y and somehow obtain the answer in terms of little f and capital F. First let us see what happens to this G when x is greater than y. To keep things concrete, I will work out the case when x is 3 and y is 2. By definition of distribution function, this is what I get. Now observe that the smallest is less than or equal to 3. X round bracket 2, which is larger, that is less than or equal to 2. Obviously, if this happens, this must happen, right? If the maximum is less than or equal to 2, then of course the minimum has also to be less than or equal to 3. So it is enough to work with only this thing. So you see, this 3 does not play any role at all because this 3 happen to be greater than 2. Now I will restore x and y in place of 3 and 2. So you see, this is actually free of x. So when I shall partially differentiate this with respect to both x and y, the partial differentiation with respect to x is going to kill it. So in this case, x greater than y, this mixed partial derivative must vanish. In other words, the density must vanish. And this happened because x and y were in the wrong order. This is always supposed to be less than this, but here x was greater than y. This wrong order killed the density. In general, when you have x1 to xn, we shall have, if the joint density of x round bracket 1 to x round bracket n, the order statistics is little g, then this is going to be 0 unless the things are in the correct order. So if there is any other permutation, in that case this will vanish. Now let us again get back to our simple example of n equal to 2 and explore what happens if the ordering is correct. So we have case 2 when x is less than or equal to y. The equality case really doesn't matter, you can put it here or there, but we want to see when the first argument is less than the second argument. Again, we shall take some numerical values for x and y to illustrate ideas. X is 2 and y is 3. This is the definition. Now, there are two factorial many possibilities. x1 could be this, x2 could be this, or x2 could be this and x1 could be this. In general, there will be n factorial possibilities. So, let's just write both of them down. Now, these two are not disjoint, so we have to use the inclusion-exclusion principle, probability of this plus probability of this minus the intersection. Let's understand how we get the intersection. x1 less than or equal to 2 and x1 less than or equal to 3, 2 is the smaller, so this is what is going to survive in the intersection. And similarly, x2 will also, only the minimum of the two will survive. Now going back to general x and y, we have, now since x1 and x2 are both IID with CTF capital F, this becomes, similarly this will be, and finally this will become. So you notice these two things are actually the same thing, only in a different permutation. So had there been 3 terms, we will get the same thing 3 factorial times. So I have written it as 2 factorial times fx fy minus fx square. Now what we want to do is take the mixed partial of this with respect to both x and y. Observe that this fellow is going to die because it does not have any y, and this thing, when partially differentiated with respect to x and y, will give rise to 2 factorial little fx times little fy. And again, it is quite easy to generalize for n things. If x1 up to xn, then the density for this case will be n factorial times product of the densities evaluated at the xi's, if all the xi's are in the right order. And we have already seen that it will be 0 otherwise. So we can find the joint density of the order statistic. So here is the complete theorem. If x1 to xn are IID with density little fx, I do not need any mention of the CDF, then the joint density of x1 to xn is n factorial times product of all the densities, if this holds, and 0 otherwise. So it is just like the joint density of x1 to xn, except that I have n factorial here and I have this condition over here. And it is quite instructive to convince yourself that if I integrate this over all the xi's, then I will indeed get 1. In this exercise, I give you x1, x2, x3 IID with this density. It is uniform over the unit interval. You have to write down the joint density of x1, x2, x3. And then you have to integrate over x3 to find the joint density of only x bracket 1 and x bracket